Hi guys, so today I'm going to walk through a simple machine learning demo where I build a support vector machine classifier using Python and scikit-learn as the main library to help us with this. I'll generate a small data set, train the model, evaluate it, and then visualize the decision boundary so you can actually see how the SVM separates the classes. This is a beginner-friendly example, but this will basically give you a visual way to see how powerful this algorithm is. So we're going to start importing the libraries, and they will be all of these libraries. I had it copied, but basically the first one will generate a data set that we'll use. The train test split will split our data that we have into a training data set and a testing data set. Then we have the actual support vector classifier. This will give us the metrics, how well our model is doing. NP will help us with some calculations, and then the last one will help us with graphs and help us visualize what's happening. So I'll generate a data set called the moons data set. This is perfect for SVMs because it isn't very linear. So we're going to start off with x, y equals moons, I believe. Yep. Noise 0.25. So basically, we're adding noise to make the data set a little bit more realistic, and then a random state so we can have reproducible results. So I'll run that, and now we will just show this information. plt.scatter. This is where we use the scatter plot. Let me make sure that that's right. Yep. Okay. pld.title. So we'll put a title. We'll just call it the moons data set. Oops. Moons. There. Boom. And then to show it, you would just do plt.show. I believe. Yep. Okay. So here we can see that each point belongs in one of the two classes, and you can't really draw a straight line between them. This is where a nonlinear SVM shines. They can create curved decision boundaries. If you can see, there's a little bit of a curve to this. So now that we have that, I will start off by doing a train and test split. So basically what we're doing is we're splitting the data into a train split, which is basically where we take some of the data and we train the model on it, and then we split it into a test data set where this model hasn't seen this data yet, so there will be no bias, and we'll see how it performs on random data for it. So we want to go x train, x test, and then y train, y test, and then train test split. Yep. And then it'll be x comma y, and then you put how much testing data you want to use. So in this case we'll do 30%, seems reasonable, and then to keep it reproducible, random state equals 0. So we'll run that. Okay, boom. So this gives us a 70% data for the training, and ideally you would like there to be a good amount of training data so we have a good model. And we also have the random state, just again for reproducibility. Now we'll build and train the support vector classifier. So you can call it whatever you want. I'll call it CLF. And then this is where SVC comes in, support vector classifier. And then kernel equals RBF gamma. Oops. We should take that out. Gamma equals auto. And then I believe that's it. And now you want to fit the classifier to the data. So as I called it here, I'll call it X train and Y train, just like that. Boom. So the kernel RBF tells the SVM to use a radial basis function kernel. which allows the model to create nonlinear decision boundaries. So because it's like this, we cannot have it be linear, as I mentioned before. So we want to use RBF for that. And then the gamma equals auto. That adjusts how far the influence of a single training point reaches. A higher gamma gives more a flexible boundary that'll fit the data more clearly. So it basically determines how rigid it'll be. So then when I run fit, we're fitting the model on this data. And now we can see how the model performs. So to do that, we would do ypred equals CLF. You're calling your model dot predict. So you're predicting it on, I believe it would be the X testing data. And oops. And then you would like to just print how it does. So print classification report, yeah. And then we're gonna put Y test and compare that to the Y prediction. So this will print out the precision, recall, F1 score, and support for each class. On this data set, you normally get a pretty strong performance considering that it's kind of already built around it. And precision tells you how often the positive predictions are correct. Recall tells us how many of the actual positive examples we identify correctly. And F1 score is kind of like a mixed metric where people use it because it's a good way to show how well a model does with one statistic. So let's see that. So we see that we're getting in the 90%, which is pretty good. And let's visualize the boundary that the SVM learned. So to do that, we'll do, this is where we use NumPy. And then we can do np.line space. And then dot min -1 x dot max and then +1. Let me just make sure that that's right. Yep. And then x. Sorry if this is taking a little bit of a long time. Dot max +1, comma 500. And then we will go oops. And then it'll be reshape x dot shape. Boom. Green. then, oops, and PLT to show. Oh, yep, did. There. So this is kind of showing how the SVM kind of goes around it. So I generated a grid of points that covers the entire area of the dataset. Then I use the SVM to predict the class for every point on the grid. And then I finally colored the regions based on the SVM predictions. The boundaries you see in the plot that are usually a curved surface or wrapping around the moons is the SVM decision boundary. This is created using the kernel trick, where the SVM essentially maps the data into a higher dimensional space and finds a linear separated there. When we project it back down to two dimensions, it becomes curved. This visually shows why SVMs are so powerful for problems that cannot be linearly classified. So that's a complete example of building an SVM classifier in Python. We generated a nonlinear dataset, trained the SVM using the RBF kernel, evaluated its performance, and plotted the decision boundary. This kind of visualization really helps you understand how the SVM is making its decisions. We also see how linear algebra is affected, specifically how this is using principal component analysis, which is an integral part of this whole thing to help us better classify and make math really applicable to the real world.